Hello, this is Daryl Corn, and this is going to be my walkthrough of part one of my final project. So let's get into it. I'm going to start with the code. Okay, so this is my Jupyter notebook for my CNN model for the RGB dataset. I've split it into um, four different scripts. So, and all of them are pretty similar. So one of the first ones should take the longest. I first bring in all my Python packages. Then here I import the Kaggle data. Um, and then here I use a lot of the code provided during the lab to split into the different classes. Um, but I go a step further and I create some test data. So the data initially only had some validation data set aside, but I wanted to make sure, we had the most accurate predictions possible. So I reserved about 97,000 files for training for the, RGB data. And then I set aside about 10,000 for validation within that. And then I use about 11,000 files that belong to the validation data. I use that as my test data. Okay, so I just wanted to be clear about that. Here, I define some early stopping. So I think those always improve my model. And then the only pre-processing that I do for the images is I rescale them to be normalized in RGB values, but I suppose I am also resizing them here to be 64 by 64 pixels. So those are the two pre-processing things I do. Here I define my data augmentation. So for my data augmentation, all I do is the random flip over the horizontal axis. Um, I didn't feel the need to flip it over the vertical because that results in cars and people being upside down. I don't think it's necessary for a self-driving car to replicate or to recognize that because ideally they shouldn't be in that position. Um, I also include some random rotation. It can rotate up to 10%, and it can randomly zoom up to 20% on the Y and X axis. So here I define my model, and I'll go into the layers a bit more later. That's more so included in my PowerPoint. And I compile the model, and look how many parameters I have, and all that fun stuff. Um, and then here I'm actually um, augmenting my data as well as rescaling it. So I've created a helper function to do that. Um, I know in the previous labs we used that data gen and flow from directory and image data generator class, but I found that that was really slow. And so this method is much quicker, and it lets me train more models in a shorter amount of time. And so when I prepare the training data set here, I make sure it's shuffled and I can choose to augment it for the experiment. And the validation and test data is not shuffled or augmented. Then here we fit the model and we evaluate the model. And then we check out the training, validation, loss, and accuracy. Um, I realize now that this says loss, but it's loss and it's accuracy. And I threw them on the same model just because we've been looking at these graphs all semester, and I think, we can consolidate them a bit and put them on the same axes. And usually it works out. Sometimes it can be a bit cluttered, but we know what they say. Okay. Uh, this script, it's pretty similar, except it's training the VG16 model. And so the only thing that's really different is that, I bring in the VG16 here, and we don't include the top layers because we want to train those ourselves. We can set the base to be trainable or not, and we can even set like it to be partially trainable. And we choose how many layers we train there. So that's all that's really different here. And then I have separate scripts for the thermal data sets for the CNN and for the VG16 model. Okay, on to our analysis. So up first, we'll talk about the CNN experiments. My model structure for this primarily consisted of three convolution layers and three max pooling layers. Um, layers. Sometimes it included a dropout layer, sometimes it included L1 or L2 regularization, but I always kept the learning rate steady at 0.001 because I haven't found that that really impacts things except for speed, and unless it's too fast, then you lose accuracy. I tried different kernel sizes as well. So most of my experiments were with the standard 3 by 3, but I also tried some mixed kernels, so 5 by 5, 4 by 4, and 3 by 3 in the different layers. And I tried some where it's all 4 by 4 kernel sizes. Data augmentation, I've already gone through this. Um, oops. Uh, I also experimented with different amounts of trainable parameters. So while I kept everything at about three convolution layers, I did experiment with about 388,000 trainable parameters, and then I tried to like multiply that by about three to get 961,000 as well to see if that would improve things. And we've got early stopping as well. So, and I also have used these structures for both the RGB and the thermal data sets. So here are my results from for one portion of the CNN RGB experiments. This is with the lower parameter count. Um, I mix and matched a bunch of different methods. So up here, we plain, this is just with only pre-processing the data, no other augmentation techniques. This one is only data augmentation. This one's with the dropout layer and data augmentation. This one's with data augmentation dropout and an L1 regularizer, so on and so forth. Um, and I found that despite even checking like if mixed kernels improve it, I found that including only a dropout layer resulted in the highest accuracy at 93.2%. I noticed that including only the dropout layer led to the highest accuracy, so I just went ahead and did that for these two experiments. But they still did not outperform just the standard dropout layer with a 3 by 3 kernel. Onto this one, the same model structure, same data set, but with about triple the amount of parameters. And I found here that actually a combination of data augmentation with the dropout layer led to the highest accuracy at 93.7%. On the next page, this page um, is using the CNN structure, but for the thermal data set with the lower parameter count. And I found that, and similar to the first page that I showed, including only a dropout layer, was led to the highest accuracy at 94%. And then finally, for the thermal data, but with three times the amount of parameters, again, including only a dropout layer, led to the highest accuracy on the test data. Okay, on to my VGEG 16 experiments. So my model structure for this was to take the VGEG 16 model, and I removed the top layers, and I slapped on two dense layers on top. And sometimes I included a dropout layer, sometimes I included regularization, same data augmentation as before. And this one, I varied the learning rates a bit. So if I left the base untrainable, I just used a standard learning rate of 0.001. But if I made the base fully or partially trainable, I figured it was best to slow down the learning rate a bit. And so this is four zeros preceding this one after the decimal. I experimented with three different amounts of trainable parameters as well. So if the base was fully trainable, that led to about 15 million parameters. If the base was partially trainable, if I left the last nine layers trainable, that gave about 13.5 million parameters. And if I only trained the two dense layers on top, that was about 500,000 parameters. Again, using early stopping, and again, we use this structure for the RGB and thermal datasets. Okay, on to the VGG16, but with the lower amount of parameters. I found here that just like before, including the dropout layer led to the highest accuracy out of all of the combinations that I tested. And when I increased the parameters, so this is with partially trainable parameters on the RGB dataset. I noticed that these models were doing much better than with only the 500,000 parameters listed in the page before. So I ran a few more experiments just to see if I could improve the accuracy a bit further. And it turns out I could by including a dropout layer as well as a regularizer. And so in this set of experiments, that combination was the highest performing at 95.5%. Similarly, with leaving the entire model trainable, um, I ran more experiments, but for this one, it was apparent that only including an L2 regularizer led to the highest amount of accuracy, although the other ones were pretty close at 96.4. This was beat it by a tenth of a percent. For the thermal data sets, with the low amount of parameters, again, the dropout layer performed the best at 92.5%. And for a partially trainable convolution base, the dropout along with the regularizers performed the best again. And they performed about evenly, whether it was L1 or L2. My last set of experiments so far, um, it turns out the dropout layer with the L2 regularizer performed the best at 96.3% and leaving the model fully trainable. So, to sum it all up, everything we've done so far. The best model structure out of the two that I've tested has been the VGG16, and it has performed well on both the RGB and the thermal data sets. Additionally, for both data sets, it was preferable to leave all of the layers trainable and have about 15 million parameters to change or to train. Um, some uh, the the different data sets required different data augmentation techniques. So for the RGB data set, I only put an L1 regularizer on that. But for the thermal data set, I included a dropout layer with the L2 regularizer. And so far, the highest accuracy that I've managed to achieve for the RGB data set is about 96.5%, whereas for the thermal, it's 96.3%. So that's what I've done so far. In the future, my future experiments, as you may have noticed, I haven't done any of the autoencoder tests. I was waiting um, for the lab results or for the lab to come out, which it was released today with some autoencoder examples. So I plan to do that in the future. I also plan to add more layers to the CNN models. I don't know why I wrote 5 to 6. Ideally, I want to get the trainable parameters up to the same amount that's in the pre-made VGG16, so up to like 15 million parameters. So this will be a lot more than just 5 to 6, I imagine. Um, and lastly, you may have noticed that I only included accuracy metrics in this discussion. I was waiting to see if we would discuss other methods a bit more before I dived into them on my own, but that's no big deal. I can just research the F1 measure, the area under the curve, or the confusion matrix, and include that in my next report. So that completes everything that I've done so far for my final project. Thank you.